Why did you try to tell everyone what answer? What is wrong with you?
All right, so for this problem, do we need this problem? Okay. Basically, this is a. Wait, okay, what is the question is asking what is the maximum velocity so it doesn't touch? This is like a projectile. This is just a projectile motion problem. That's all it is. It's like a kicking the soccer ball problem with a maximum height. That's it. Right? Because normally under gravity, the acceleration down would be 9.8, right? Would be g.
Yeah.
But here, the acceleration down is just a function of the electric field. Because we know that F is EQ, right? So, and then EQ is equal to MA, so it pushes down. But we can do all of that, otherwise. So if we have this, let's see, if I crack this vector, so if I just look at this, maybe I don't have any idea what to do, but I see a vector at an angle. So I go, okay, that's not acceptable. So I will crack it. And when I crack it, we get V0 cos 45 and V0 sine 45. So let's see. What do we know in terms of energy? Did they say what this particle was? Of an electron. Excellent. That's good. That is very helpful. So this is an electron, right? So its mass of the electron is 911, emergency, minus 31 kilograms. And we know its charge, in fact, is negative 1.6 times 10 to the minus 19 coulombs, right? So technically what I could do here, if I wanted to, is I could say the sum of the forces in the y are equal to ma. And the only force is the electric field force. That's going to be EQ is equal to ma. So A is equal to EQ over m. If I wanted to do that, I could. And now I have exactly a two-dimensional motion problem, where I have the initial velocity being this, right? I know the final velocity at the top vertically will be 0, yes? Because if it isn't 0, it's going to hit this, right? Because in order to make it come back down, there must be some point where it stops and comes back down, yes? Throw something up, comes back down. So I know the final velocity is 0, I know the distance, and I know the acceleration, so we can find V0. Right, so just to be clear, if I wanted to do that, I would use Vf squared is equal to V0 squared plus 2ax. Okay, that's simply one way that we could do it. The way that I think might be a little bit better would be something using, say, energy or something, but either way it works. Okay, so if we were going to use energy, actually, can I vectorialize it? Can I look at energy in that dimension? Yeah, because the energy, okay. What I'm thinking about here is I'm thinking in my head, there's a velocity in both directions. So there's going to be energy, like this kind of energy both ways. If I use the energy vertically, like if I just pretend like this is being thrown straight up at this initial velocity of v sine theta, then that will allow me to come up with a value that I can set equal to v sine theta, and then of course go back to extrapolate and get this. So if I wanted to, I could say in the y dimension, and the reason I can say this is because in the x dimension, nothing changes, right? There is no acceleration in the x direction. So the kinetic energy that's in the x direction will always be the same. So in the y dimension, we can say something like, actually I'm wondering if this works, but I'm going to try it. Something like that. Okay, and so we're saying that this initial kinetic energy is going to equal the potential energy up here. And does it make sense to you that if I take an electron and pull it this way, I'm storing potential energy? Does that make sense to you? Right? Because if I just said, okay, I have an electron here, where does that electron want to be? It wants to be down here on the bottom plate. So I have to do work to pull that electron up to the other plate, right? And if I let it go up here, boom, it would come back down. So we're kind of, just like gravity, we're kind of saying that the amount of potential energy that it took to lift it up there is going to equal the kinetic energy that it had at the bottom if it barely reaches the top. Does that make sense? Yeah.
Why so
Okay, do you see the arrows? What do those arrows represent? Yeah, the electric field. And what do electrons do in an electric field? What do electric fields do to all charges? What was the basic fundamental concept of electrostatics? The basis of this whole chapter. Okay, so opposites attract, likes repel, right? That's the basic fundamental concept. And what does that? What allows them to attract and repel? Yes, electric fields. Electric fields are the hands and feet of that desire to be attracted and repelled. Okay. So now, how do electrons behave in electric fields? We know that an electric field is going to push or pull an electron. Okay. So in general, how do electrons behave in an electric field? They go, against the flow. Right? Against the flow. See how the field flows up? The electron goes against the flow, so it will go down. And so a proton would go with the flow. Think of positive people, right? They're like, whatever. You want to go to Applebee's? Whatever. That's fine. I'll go with the flow. Right? And then think of negative people. You want to get Applebee's sucks. I hate their food. It's too expensive. I'm not going to Applebee's. Okay. Now Applebee's is going to sue me for libel on this. All right. Anyways, so we have 1/2 mv, and this is, I'm going to call this vy0 squared, because this right here is equal to vy0. Do we get that? I don't want to put v0 because I want you to understand I'm talking about this entire amount here. Right? Vy0 is this vertical component. And then that's going to equal, and what is the potential energy there in an electric field? Well, how do you get it? Let's see. We have, I think it's just ED, right? Yeah, so we can check this out real quick. We can do this in our head. We remember that Coulomb's law is about this. Potential energy is equal to Coulomb's law times r, times distance, right? And then to get, so that's pretty much it. It's just ED. So then this becomes, well, and what is the electric field? The electric field is kq over r squared. So if we do the potential energy, which is k q1 q2 over r, how do we get, what do you multiply times E to get that? Yeah, it has to be QR, yeah. That's weird. Yeah.
What are you doing?
I'm trying to find the potential energy here. The electrical potential energy. Because we have the equation. Oh, I know what we can do. We can just do the work, the electrical work. That works. So how much? Oh, hello. John, boy, you're popular. So how much potential energy is there in this? Like, how do you get the potential energy that it has when you lift it up to there? So if we looked at, and that's what I was doing here. I was trying to find out what do I need to multiply it by. So if I multiply the electric field strength, which I know, by Q and R, then I get the potential energy. Does that part make sense? Right? We can also say, I was also saying you can come up with the work in the electric, done by the electric field, right? And that work is going to be the force of the electric field times the distance, right? And then that's going to end up to be the same, see, because these are the same.
Yeah.
Yeah.
I was just asking because for us, like Dr. and I, we were talking about force.
Uh-huh.
And we were talking about the
I'm sorry, speak up, Alice, that last part.
Well,
Talking about work.
Governor was talking about work.
Uh-huh. Oh, okay, so do you see both of them work? Both of them work, right? Yeah, you can use work, you can use the potential energy, either way it works. Okay, so if we use the work, we have to use the force of the electric. Well, actually, watch. Let's do that. This is the force of the electric field times the distance, right? And what is the force exerted by this electric field? Because isn't the F equal to EQ? And so we get exactly the same thing, because the force is EQ times D. EQD, EQR, whatever, same smell. Okay, so then we get 1/2 m Vy0 squared is equal to EQD. And now it's just a matter of solving out for this, right? Because you can say that Vy0 is equal to the square root of 2EQD over m. And then you take this Vy0 and set it equal to V0 sine 45. So I guess essentially, if you just divide this thing, or multiply this by 1 over sine 45, then you'll get your answer for this. This will actually come out to be V0. Okay? So let me walk through that again with the energy to make it a little bit more clear. What I'm saying is the kinetic energy initial is going to equal to the potential energy at the top. So I've got 1/2 mv(y0), that's the initial velocity in the y dimension, squared, and that's going to be, this came out to be, came out to be EQD. And then if we remember that Vy0 is equal to V0 times whatever, sine of theta. So then that allows me to say 1/2 m V0 sine theta squared is equal to EQD. So then we can get V0 sine theta is equal to the square root of 2 EQD over m. Take this, put that over that, and we get our answer. So that's that approach in a nutshell. So remember, we have this is the energy approach, and then this E equals EQ over m and all that stuff, this was the kinematics approach. Now, what might be fun is let's do this. Oops. I didn't pick up some of the stuff that I needed to pick up. Okay, so we'll keep our energy approach right there, and let's just have some fun with the kinematic approach, right? So we know that based on the kinematic approach, we have our V0.
Whoa. It's offense.
I think so. I don't think so. It's one of the Patriots.
Oh, hey.
See?
Same row though, same row, or all of them. Okay, our V0y is equal to V0 sine theta, okay? Our VF is equal to 0. Our A is equal to EQ over M. Yes, distance. And we have a distance, right? We know a distance. Our distance is given. Here we go. X is D. Okay? And then we know that our equation is VF squared equals V0 squared plus 2AX. So now we can say V0 is equal to the square root of what, negative 2AX? Why does that come out to be negative? Whatever. Huh? Oh yeah, because our acceleration should be negative. Sorry. There you go. Because our d is positive, so our acceleration should be negative. And that's going to work out. So now we plug this in, And remember our V0, this is our V0y actually, right? This is going to be V0 sine theta. Under our square root, we have 2a, which is EQ over M times x, which is D. Okay, now I just take this, put sine theta here, and then let's compare these two. All right, do we see these two are the same? Yes, I did.